This data visualization maps out our orbital space, scaling up from a handful of early historical satellites to the dense, buzzing swarm you see today, a constellation of over 14,000 active machines. By highlighting these specific pathways and tracing them down to terrestrial data nodes, we can see how entirely dependent we are on this architecture. It powers global GPS, directs high-speed internet to remote terrain, and delivers the climate monitoring data that manages global agriculture. Human lives are suspended in this traffic jam. Astronauts live and work aboard the International Space Station, right in the crosshairs of low Earth orbit. We have tethered our modern technological existence to a fragile, invisible web in the sky. If it collapses, our terrestrial infrastructure collapses with it. Researchers track a metric known as the crash clock to measure the stability of this environment. It calculates exactly how long we have until a catastrophic collision occurs if our automated dodging systems suddenly fail. Right now, that clock sits at just 2.8 days. In low Earth orbit, objects travel at roughly 17,000 miles per hour, about 7 times faster than a rifle bullet. At those velocities, even a stray bolt strikes with the kinetic energy of a bomb. This extreme physics sets the stage for a theoretical threshold proposed by NASA scientist Donald Kessler. He calculated that if orbital density reaches a certain critical mass, a runaway disaster becomes mathematically inevitable. A Kessler event triggers when 2 multi-ton objects collide at hypervelocity. As this simulation illustrates, the impact instantly vaporizes the satellites, shattering them into a rapidly expanding cloud of high-speed shrapnel. Because satellites orbit at intersecting diagonal angles, this initial shrapnel cloud cuts directly across other active highways. Those fragments strike more satellites, instantly multiplying the debris in a self-sustaining chain reaction. Down on Earth, the fallout would be immediate. Navigation grids would fail, global communications would black out, and a dense, impassable shell of metallic junk would form a barricade around the planet. The Kessler syndrome would halt all human spaceflight and trap us on our own world. In a matter of days, we would lose the digital nervous system of the 21st century. This schematic illustrates our primary line of defense, autonomous AI. Because human operators cannot react fast enough, satellites now automatically fire their thrusters to alter their trajectories when an algorithm predicts an incoming debris path. Today, this automated dodging relies entirely on a vast global monitoring infrastructure. Ground-based radars and telescopes track millions of objects, feeding real-time positional data up to the satellites. But this tracking system has a glaring vulnerability. When intense solar storms hit the Earth, visible here as brilliant auroras, they heat the upper atmosphere, increasing drag and scrambling command links. When a solar storm blinds these algorithms, the actual position of a satellite can drift miles away from its predicted location. The AI loses its ability to see incoming threats, leaving the satellite completely defenseless. Forcing thousands of satellites to execute automated dodges is a temporary patch. It cannot sustain an orbital environment where the volume of high-speed hazards grows exponentially every year. To fix the blind spots in our tracking networks, aerospace engineers and the military are pushing for advanced space domain awareness, the ability to monitor the debris that ground-based radars simply cannot see. One solution involves launching tandem satellites, like the Red Wing and LISA projects. By flying in close formation, they can maintain persistent surveillance over the polar regions of low Earth orbit, where terrestrial sensor networks struggle to reach. Simply identifying the debris is insufficient for safety. As astrophysicist Neil deGrasse Tyson points out, satellites launch from various latitudes and cut diagonally across one another, turning orbit into a high-speed racetrack with thousands of intersecting paths. Navigating this environment requires international cooperation. We need to establish global space traffic lights and rigid rules of the road before these orbital highways gridlock completely. Even with perfect tracking and strict rules, dodging is a defensive game. To actually defuse the threat, we have to start actively removing the largest, most dangerous pieces of dead hardware from orbit. Enter the orbital tow truck. The European Space Agency's ClearSpace 1 mission is currently in development to serve as a specialized spacecraft built to hunt down and capture derelict rocket bodies. This simulation demonstrates the intense mechanical challenge involved. The tow truck uses AI targeting to match the exact velocity of a tumbling multi-ton object, deploying robotic tentacles to safely grip the debris at 17,000 miles per hour. Engineers are testing other capture methods as well. Some designs feature spacecraft that deploy massive, expanding nets to ensnare loose, erratic clouds of shrapnel. Perhaps the most aggressive prototype relies on ballistics. It fires a specialized tethered space harpoon that pierces the thick aluminum chassis of a dead satellite, locking in so it can be reeled away. But there are millions of pieces of lethal debris in orbit. Launching a multi-million-dollar tow truck to capture them one by one is an economic impossibility. It simply will not scale to the size of the crisis. To secure the future of space exploration, we have to treat the root cause. The aerospace industry must shift away from single-use hardware and adopt a circular space economy. This requires a shift in engineering principles. Satellites must be designed for modular disassembly, and every launch must include fuel and a strict protocol to safely deorbit and burn up in the atmosphere when the mission ends. For systems parked in geostationary orbits too high to be dragged down, the protocol requires them to use their final reserves to boost outward, parking securely in designated zero-debris graveyard orbits. Orbital space is a finite, delicate ecosystem. If we want to remain a spacefaring species, we have to ensure that our orbital infrastructure cleans up after itself.